In the next example, we're going to look at a function. We're going to create a function that has a limit at every point in its domain except for one. So we're first asked to create that function and then prove that the function does not have a limit at that particular point. So specifically, the directions say, find a function whose domain is the interval 0 to 1, open, going into the reals. It has a limit at each point in that interval 0 to 1, except for one point. And then prove that the limit does not exist at that one point. Well, a nice, easy one to select would be something that looks like this. We take this, you could think of it as a piecewise function. It's obviously continuous. No, I'm sorry. The limit exists everywhere in between 0 to 1/2. And the limit exists everywhere in between 1/2 to 1. Where the limit does not exist is at the one single point 1/2. So this is how we would write this function f of x. F of x is the height of 1/2, or the value of 1/2, for all x in between 0 and 1/2. And then from 1/2 to 1, including 1/2, the function value is 1. So first, let's look and remind ourselves what the limit of the definition at 1/2 means. The limit of f of x as x approaches 1/2 is equal to the number capital L, a real number. What that means, this limit equation, means that for every epsilon, there exists a delta, such that as long as x is in the domain, 0 to 1, and the distance from x to 1/2 is less than delta, then the distance between f of x and the limit L is less than epsilon. That's just the definition, Epsilon-delta definition. But the limit does not exist at 1/2. So the limit of f of x as x goes to 1/2 is not equal to L means, and I need to point out there's two cases here. Either this means that the limit doesn't even exist, or it means that the limit exists, but it is something different from the number L. So if you remember how to negate, for every becomes there exists a delta greater than 0. There exists is going to become for every delta greater than 0. And now we need to negate this, which is like P implies Q. Remember, P implies Q? Well, to negate that, to make it false, we have to make P be true. So I need x in 0, 1, and this is also true, but this is false. So I make P true and Q false in this implication. That's how you negate an implication. Make the first one true, make this part false. And I'll use the word and or but. F of x minus L is greater than or equal to epsilon. So for every epsilon we're given, there exists an epsilon such that for every single delta greater than 0, I can find an x in the domain and very close to 1/2, but f of x minus the limit is greater than or equal to the epsilon. So we're going to use this line to prove that the limit doesn't exist. Okay, since I've worked this out, I know I can use this value of epsilon, 1/4. In this case, 1/4 happens to be half of the distance between the heights of these two line segments. And we'll just say let delta greater than 0 be given. Doesn't matter what it is. Okay, so we've got our epsilon, we've got our delta. Well, now what I want to do is I'm going to choose 2 points. How about let x1 and x2 be in the domain. And I'm going to put a restriction on this. Let's say where I'm making this too wordy. Let me just say let x1 be in the interval from 0 to 1/2. Let me see. Let's change that again. Here's what I want. Here's 1/2, here's 0, here's 1. I want to choose x1 to be within, let's see, this would be 1/2 minus delta. This would be 1/2 plus delta. I want to choose x1 to be in this region and x2 to be in that region. So I'm going to say let x1 be an element of 1/2 minus delta to 1/2. That puts it right in the left half of this interval. And then x2 is going to go from 1/2 to 1/2 plus delta. So we've got x1 in this region and x2 in that region. That guarantees that they are both within delta of, they're actually within they're within delta of 1/2. All right, so for those 2 points, I'm going to say first, notice that f of x1 is equal to something and f of x2 is equal to something. Well, x1 is to the left of 1/2, so f of x1 has a height or value of 1/2, where f of x2 has a height of 1. All right, well, let's then say that by my definition of x1 and x2, we know that this is true. So we've got this being true, right? That's true for x1, that's true for x1, and it's also true for x2. So again, that just simply says that neither one of them is equal to 1/2. That's why we have this 0 here. x1 being to the left of 1/2, actually in this region, it's within delta of 1/2, and x2 in this region is within delta of 1/2. All right, so I'll put, can I use a therefore? Yeah, I think I can use a therefore. This will be a long sentence, but the last sentence. Therefore, f of x1 minus L plus f of x2 minus L. And maybe on that one I'm going to write it backwards. You'll see why in a minute. It doesn't matter since it's an absolute value and it's a difference. It doesn't matter which way I write it. Well, we know what this is equal to. I'm going to do a little bit of absolute value arithmetic on this. F of x1 plus minus L plus L minus f of x2. And why am I able to say this? Well, it's not equal, greater than or equal. Why am I able to go from here to here? That's by the triangle inequality in reverse. Normally, we start with something like this, and then we break it up into two, the sum of two absolute values, and we say it's less than or equal to this. So we're just doing the exact same thing, but in reverse order. This is less or equal this by the triangle inequality. But this is just, the L's cancel, f of x1 minus f of x2 in absolute values. And we know exactly what that is. That's 1/2 minus 1 in absolute values, which gives us 1/2. So if this plus this is greater than or equal to 1/2, that means one of them has to be greater than or equal to 1/4. Two positive numbers being added together, they give you at least 1/2. One of them has to be at least half of that, which is 1/4. So that's 1/2, which implies what I just said, that either f of x1 minus L is greater than 1/4, or f of x2 minus L is greater than or equal to 1/4. And that's the end. All we had to do to prove this is that there exists an epsilon. I chose 1/4. I could have chosen any number smaller than that. Such that for every delta, so I chose an arbitrary delta. Since I didn't give it a value, it means it works for every delta. All we had to do was find one value of x that's in this interval and very close to 1/2 within delta of 1/2, but f of x minus L is greater than or equal to epsilon. And our epsilon was 1/4, so we found one. I don't know which one it was. It was either x1 or x2, but one of them has this value in absolute values, f of x minus a limit greater than or equal to epsilon. And we're done.